Next, let's look at an example problem where we apply Kirchhoff's rules. We want to know what is the current in the 8 ohm resistor in this circuit. So first let's reproduce this circuit so that we can annotate it as we go along. So in this circuit we have a 16-volt battery. We also have a 4 ohm resistor, and this is on the top branch. Then on the next branch down we have a 18-volt battery, and we have a 12 ohm resistor. And then finally on the bottom branch of the circuit we have only an 8 ohm resistor, and that's the resistor that we want to find the current through. Alright, so there is our circuit. The first step in solving Kirchhoff's laws is to find the junction points. Find the places where currents branch off or come together. So this circuit has 2 junction points. One is here, and then one is here. So those are the junctions in our circuit. The next step is to pick current directions and label currents through our circuit, remembering that currents go along a branch from junction to junction. So I will choose as current 1, or I1, the current going through the top branch. So I1 then goes from junction to junction. So here is my I1, and I don't know for sure that the current is flowing in this direction. I'm just guessing at this point, and it's okay to guess. If I get it wrong, I'll just, when I solve the equations, that current will happen to be negative, but it agrees with what I've drawn, so I keep it that way. So the next current that I'll draw is on the lowest branch. So from junction to junction, I'll call that current I2. Then finally, the middle branch, I'll have a current going from junction to junction. I'll pick this direction and call that I3. So I've done the next step of picking the current directions and labeling the currents. So then the next step is to apply the junction rule. So I need to pick a junction and sum the currents going in, set it equal to the sum of the currents going out. So I guess I'll pick this junction here. I would pick one of the two. I'll pick this one. And I have 2 currents going in, I1 and I3. So I add them together, and the sum of the currents going in is equal to the current going out, which is I2. So now I've applied the junction rule. Next, I'm going to need to apply the loop rule to 2 of the 3 possible loops in this circuit. So first I'll go around the full outer loop. And we could pick any of the loops, but I'll go around the full outer one. And if I do that, then if I go around this full outer loop, then first off, if I go clockwise, I could go counterclockwise as well, it doesn't matter. But if I go clockwise around this full outer loop, I would first hit this battery, and I hit the negative terminal first, which is the shorter side. So since I hit the negative terminal first, I would write down minus 16 volts. I can just leave that as a number. These are all going to be voltages, so minus 16. Then I'm going through the 4 ohm resistor, and I'm going with the current I1. So I would write down plus 4I1. Then I would be going through the 8 ohm resistor, and I'm going in the direction of the current. So I would write down plus 8, and this is I2 that goes through the 8 ohm resistor. And then I'm back where I started. So the sum of those voltage changes is equal to 0. Okay, so that's what I get from going through the full outer loop. Next, I need another loop rule equation, so let's go through the lower loop. So if I do that, starting here, I first hit the negative terminal of the 18-volt battery, so I write down minus 18. And then I go through the 12 ohm resistor with the current, so that's plus 12I3. And then I go through the 8 ohm resistor with the current. So that's plus 8I2. And now I'm back to my starting point, so the sum of those voltage differences is equal to 0. So now I have the junction rule and the loop rule equations that I need. So I have 3 equations, 3 unknowns. I need to solve for my unknown currents, I1, I2, and I3. So the next thing that we can do to solve this algebraically is, a good strategy is to figure out what variable do all 3 equations have in common. So I have an I1, an I2, and an I3 in this first one. And in the second equation, I have an I1 and an I2, and in the third one, I have an I3 and an I2. So the I2 is common to all 3 equations. All 3 equations have an I2 in them. So then the strategy is to take 2 of these loop rule equations and solve them for the other thing. So this first equation here, I'm going to solve for I1. So I'll have I1 equals something with I2 in it. And then I'm going to take this second equation and I'm going to solve for I3, because then I'll have an equation where I3 is equal to something with I2 in it. So I have I1 is equal to something with I2 in it, I3 is equal to something with I2 in it, and then I can plug that into the first equation and have an equation that just has I2. And then I can solve for I2 and then solve for the other ones as well. So let's follow that strategy. Let's first take this equation here and solve it for I1. So if I do that, I have 4I1 is equal to 16, moving this to the other side, minus 8I2. And then I can divide through by 4, so I1 is equal to 4 minus 2I2. So now I have an equation. I have an equation for I1. So the next thing I'm going to want to do is take this second equation and solve it for I3. So if I do that, I have 12I3 is equal to 18 minus 8I2. And then I would divide both sides by 12. So I3 is equal to 18 minus 8I2 divided by 12. So it's tempting at this point to move numbers into decimals, but it turns out if you do that, rounding errors accumulate rather quickly, and which can really move your final answer off from anything that Learning Hub will accept. So it's really best to leave things as fractions as you solve these equations. I can simplify this a little bit. I can divide everything in the numerator and the denominator by 2, in which case I would get 9 minus 4I2 divided by 6. And then I'll just leave it like that. All right, so then I have an equation for I1 and I have an equation for I3, and I will plug those equations back into my loop rule equation. So the loop rule equation says that I1, well, I know that I1 is the same as 4 minus 2I2 plus I3, but I3 is the same as 9 minus 4I2 divided by 6. That's going to be equal to I2. So now we see we have just an equation with a single unknown in it that we can solve for. So first what I'll do to get rid of this 6 in the denominator, I'll multiply everything through by 6. If I do that, I have 6 times 4, which is 24, minus 12i2. The 6 cancels with the 6 here in this term, so then that gives me plus 9 minus 4i2 is equal to 6i2. So now I need to gather up all of the i2's and gather up all of the terms that do not have an i2 in them on the other side of this expression. So if I add together the 6i2 plus the 4i2, that gives me 10, and then I have an additional 12, so that gives me 22i2, and then that's going to be equal to 9 plus 24, which is 33. So that gives me 33 is equal to 22i2, and so therefore i2 is equal to 33 divided by 22. I can divide the numerator and the denominator by 11, so that's the same thing as 3/2 of an amp. So I2 is equal to 1.5 amps. So I should have 1.5 amps for I2, and lo and behold, that was the current that I was looking for. So that is the answer to this problem. Now, if I need to know what I3 and I1 are, I can simply take this 1.5 amps and plug it into this equation to find I1, or plug it into this equation to find I3. So let's go ahead and do that. So I1 is going to be equal to 4 minus 2 times I2, but I2 was 3/2 of an amp, and the 2 cancels with the 2 here, so that would give me 1 amp for I1. And then if I were to solve this equation for I3 by putting the value of I2 in, then I3 is going to be equal to 9/6 minus 4/6 times I2, but I2 is 3/2, and let's see, if we cancel the 2 here, we have 9/6 minus 6/6, which ends up being 3/6, or half. So that would be 0.5 amps. So now we have values for all of our currents.